Good evening, dear students. Myself, Professor Tejaswini Chetty, back with another numerical on Z transform. Dear students, so far we have discussed the definition of Z transform, how to determine the Z transform of the right-sided signal, and the inverse Z transform methods. So now today we are going to study some of the formulas in order to perform the numerical further. As you all know that the transfer function of an LTI discrete time system. Dear students, I hope you remember in the second unit we have discussed the transfer function of the LTI continuous time system. So similarly same here we are going to discuss about the transfer function of LTI discrete time system. As you all know, the transfer function, it is the ratio of output to the input. But here in Z transform, the definition is, it is the ratio of the Z transform of the output to the ratio of the Z transform of the input. And it is given by H of Z is equal to Y of Z by X of Z. And the next point is impulse response of LTI discrete time system. We all know that for a discrete time system, the impulse response is represented by H of n. So now H of n is equal to inverse Z transform of H of Z. As we all know, H of Z is nothing but Y of Z by X of Z. So, impulse response of LTI discrete time system H of n is equal to Z inverse of H of Z, that is Z inverse of Y of Z by X of Z. And next is response of an LTI discrete time system using Z transform. As we all know that response is nothing but output. So here the output of a discrete time system using Z transform is given by Y of n is equal to YZI of n plus YZS of n. Dear students, again I would like to recall the LTI continuous time system using Laplace transform. I hope you remember the Laplace transform. In that we have done y of t is equal to yzi of t plus yzs of t. Similarly here in discrete time system using Z transform, the response is given by y of n is equal to yzi of n plus yzs of n. So dear students, you already know that this is y of n is the complete response of the discrete time LTI system, and where yzi is nothing but zero input response of the system and yzs is nothing but zero state response of the system. Next we are going to see the formula. The input output of an discrete time LTI system is given by, that is summation m equal to 0 to n a to the a m into y of n minus m, which is equal to summation m equal to 0 to capital M bm x of n minus m. This is nothing but output is equal to input. Let's take this as equation number 1. And now we'll see how to determine the yzi of n. Yzi of n is nothing but it is the zero input response of the system. Here system means discrete time LTI system. And we have already discussed in the second unit that the zero input response is also called as free response or natural response. So yzi of n is also called as free response or natural response. Now let us discuss that how we will get the zero input response. The first step is we have to put n is equal to 0 in equation number 1. We have to put x of n is equal to 0 in equation 1. We have to put x of 0 equal to equation 1 and substitute y of n is equal to y zi of n. Therefore, in equation number 1, the right hand side of the equation will be equal to 0 because we are taking x of n is equal to 0. Hence, the right hand side of the equation number 1 will become 0. Therefore, summation m equal to 0 to n am y zi of n minus m equal to 0. So, the right hand part becomes 0 because we are substituting x of n is equal to 0. Why we are substituting x of n equal to 0? Because in order to determine the zero input response, the first step is that we have to take x of n is equal to 0, and the second step is we have to replace y of n by y zi of n. So after this, what we have to do? We have to take the z transform of the equation with non-zero initial conditions for output. Dear students, we have already, again I am going to recall you, we have already discussed what is non-zero initial condition and zero initial condition in detail in the unit 2. So after taking the z transform, we will get equation y zi of z is equal to something. Then the zero input response y zi of n of a discrete time system is given by taking the inverse z transform of y zi of z. So finally y zi of n will get from y zi of z. That is, by taking inverse z transform of y zi of z, we will get y zi of n. So next part is zero state response. As we all know that it is denoted by y zs of n, and the zero state response is also called as forced response of the discrete time LTI system. So here it is the response of the system due to input signal and with zero initial output. It is the response of the signal due to the input signal and with zero initial output. So here how we will determine the yzs of n is that the first step is that substitute y of n is equal to yzs of n in equation number 1. We will substitute yn of is equal to yzs of n, and by taking the zero initial conditions for output and non-zero initial conditions for input. So after this, for this equation we will take the z transform, and after that we will get yzs of s, and by taking the inverse z transform of yzs of z, we will get yzs of n. So dear students, these are some of the basics of the transfer function, LTI system for transfer function, and the output response of an LTI system, and what is the impulse response of an LTI system. Now let us discuss some numerical. So dear students, this is the numerical. The numerical is determine the impulse response h of n for the system described by the second order differential equation. Here we have to find the impulse response, that is h of n, and the given is the input output equation of a discrete time LTI system. So here the equation given is y of n minus 4yn minus 1 plus 4yn minus 2 is equal to x of n minus 1. So now the given equation is a second order difference equation of a discrete time LTI system. So for this equation, we will take the z transform with zero initial condition. That means we are going to apply the z transform with zero initial condition for the given second order difference equation. So in the next step, here I have applied the z transform for the equation. So here we know that the Z transform of y of n is nothing but y of z, and the Z transform of y of n minus 1 is z to the power of minus 1 into y of z plus 4 z to the power of minus 2 into y of z, which is equal to z inverse of x of z. Dear students, again I am going to recall you all the Laplace transform method. Dear students, as you all know that if it is d square y of t by dt square, then the Laplace transform of d square y upon dt square will be s square into y of s. I hope you all remember. Similarly, same here, we are going to apply the z transform for 0 initial conditions for the given equation. So after applying the z transform, z transform of y of n is y of z, and z transform of y of n minus 1 is z to the power of minus 1 into y of z. Similarly, z transform of y of n minus 2 is z to the power of minus 2 into y of z, which is equal to z inverse of x of z. So from this equation, we will get y of z by x of z. So here y of z by x of z is equal to z inverse by 1 minus 4z inverse plus 4z to the power of minus 2. So dear students, we have already discussed that y of z by x of z can also be written as h of z, because y of z by x of z is equal to h of z, where h of z is the transfer function of the system. So h of z is equal to z inverse of 1 minus 4z inverse plus 4z to the power of minus 2. So after evaluating all this, we will get z square upon z into z square minus 4z plus 4. So the z get cancels. So we will get h of z is equal to z upon z minus 2 whole square. Why z minus 2 whole square? Because this is z square minus 4z plus 4 can be written as z minus 2 whole square. So we will get h of z is equal to z upon z minus 2 whole square. Now we will write this in terms of multiplying and dividing by 2. We will write 1 by 2 into 2z upon z minus 2 whole square. Why we are taking multiplying and dividing by 1 by 2 means, in order to get the standardized form, that is, we can directly apply the z transform properties. So next, as we all know that the impulse response can be determined by taking the inverse z transform of h of z. Therefore, the impulse response h of n is equal to z to the power of z inverse of h of z, that is z inverse of 1 by 2 into 2z upon z minus 2 whole square. So I will take 1 by 2 common outside, and z inverse of, that is z inverse z transform of 2z upon z minus 2 whole square. Or I can write, we note, dear note, this is one of the property, that is z transform of n into a to the power of n into u of n is a into z upon z minus whole square. Since therefore we can directly write 2z by z minus 2 whole square can be written as n into 2 to the power of n into u of n. Why 2? Because z minus 2 is nothing but it is in the form of z minus a. So n into a to the power of n, where a is equal to 2. So 2 is a. So 2 to the power of n into u of n, or I can write this as h of n is equal to n into 2 to the power of n minus 1 into un, because this 1 by 2 can be written as 2 to the power of minus 1. So h of n is equal to n into 2 to the power of n minus 1 into u of n. So by this we will get the impulse response of the given LTI system determined by the difference equation. Thank you.